Alright, next up, video 2. Why is it that the area under a curve corresponds to an antiderivative? So I'm going to draw a picture. Here's my axes, my y-axis, my x-axis, and we'll draw a curve. Doesn't matter, it's some curve, doesn't matter what kind of curve it is, as long as it's continuous. And we're going to look at the area under this curve from x equals 0, nothing special about 0, just makes the math a little bit easier, to x. So imagine this is a slider. You're sliding this across, changing the amount of area that's contained underneath the curve. I'll use this sparkly pink pencil to shade in the area. Okay, and I'm going to, because that area is a function of x, we move x a little bit, area changes a little bit. I'm going to call, and this function is f of x, I'm going to call this area here a as a function of x. Okay, and we know already how to get an area from later in the course. The area as a function of x is going to be equal to the integral from a to b, so from 0 to x, of f of x dx. And strictly speaking, I should say f of t dt. So I'll write that beside it. Should say a of x equals integral from 0 to x of f of t dt. But we're going to be badass and not do that. We're just going to say this is a curly x and that's a straight x, or vice versa, it doesn't matter. What happens if we add a little tiny bit of extra in the x direction? What if we move the slider a little tiny bit? Let's draw what that looks like. Okay, I'll try to do my best to draw the same function, the same curve. And we're looking at a little bit of extra area. So here was x. Draw a dashed line up from x. And here's the little bit of extra where we're going to add x plus h. We're adding a little bit of extra of width h. Now this is the area we're looking for. Okay, and it's the same curve f of x. And if this first one was the area from 0 to x, we call that a of x, and the second one is the area from 0 to x plus h, this will be a of x plus h. Okay, what's the relationship between a of x plus h and a of x? Let's look at this little extra bit that we added. So let's do highlight the extra bit. Let's use left-handed rectangles to approximate the extra piece we're going to use. You can use right-handed rectangles, but it's better to use left for this particular setup that we have here. We're setting up the problem so that left-handed rectangles are going to be easier to make sense of. So we're evaluating the height of the rectangle at the left endpoint of the rectangle. The height of the function is going to be f of x, the value of the function at this x value. So rectangle, I'll draw it down here. The height is f of x, and the width is h. We're going from x to x plus h, and so the difference, the change in the x value, is just h. So we're looking for this little extra bit here. This extra area, the area of this extra rectangle, is h times f of x. Okay, so let's look at these three pictures and see if we can write down a relationship between the second area and these two areas, top and bottom here. A of x plus h is going to be equal to a of x, the first region, plus the little extra rectangle, and it's going to be approximately equal to. There's an approximation because we're missing this little bit up here. So approximately equal to a of x plus h times f of x. That pen's dying, just like my pens in class. Okay, if you want to, let's rearrange this. So we're going to have h times f of x equals a of x plus h minus a of x. So just rearranging, bringing the a of x over to the other side. Now let's, this is approximately still approximate, not equals, approximately equals. Now let's divide both sides by h. So f of x approximately equals a of x plus h minus a of x all over h. Now let's think, how would we make this exact? How do we make f of x exactly equal to this expression? So go back to here. If we make this width infinitely thin, then the extra bit that we're missing up here will go to 0. So we can make this a rectangle approximation, just like we did before for the actual integrals we were doing. We can make the rectangle approximation exact. So we write that mathematically by taking the limit as h approaches 0. Now that approximately turns into exactly equals a of x plus h minus a of x all over h. Now, go back to the beginning of the course, near the beginning, and what section was that? Right before, I think at the beginning of chapter 3, where we defined the derivative of a function. So recall. Sorry, assistant. No laughing. Recall that g prime of x equals limit as h approaches 0 of g of x plus h minus g of x all over h. So that was our definition of the derivative. What do we have up here? This equals, so f of x equals the derivative a prime of x, the derivative of the area function. So the area function then, a of x, if f of x equals the derivative of the area function, then the area function is the antiderivative of f of x. And what's an antiderivative? A of x equals the integral of f of x, evaluated from 0 to x dx, even though we should do the thing with the t and the dt. And that's what we've been using all along when we're calculating these areas. Areas between curves would be top function minus bottom function integrated from a to b. And that's why there's a correspondence between areas under curves and antiderivatives.